Now we are going to study second chapter, Gravitation. In this chapter we are going to study the many concepts regarding gravitation. This chapter gives us the idea about how artificial satellites are launched, what difficulties arises while launching the artificial satellite, what is the velocity and time period of satellite moving in circular orbit around the earth. Similarly, variation of acceleration due to gravity with uh, height, with depth, and with latitude. How acceleration due to gravity varies, that we are going to study in this chapter. Similarly, we are studying the binding energy of body at rest on Earth's surface and binding energy of satellite revolving in stable circular orbit around the Earth. First, we study the Newton's law of gravitation. For any two bodies existed in universe, there is a gravitational force acting between them. This gravitational force of attraction between two bodies is directly proportional to product of the two masses and inversely proportional to square of distance between them. If m1 and m2 are two bodies separated by distance r, then force acting between these two bodies is directly proportional to product of the two masses m1 and m2 and inversely proportional to square of distance between them. This is the Newton's law of gravitation. Newton's law of gravitation mathematically can be expressed as F equal to capital G m1 m2 upon r square, where capital G is gravitational constant and its value is always constant throughout the universe. G equal to 6.67 into 10 raised to minus 11 Newton meter square per kg square. Dimensions of G. We know that according to Newton's law of gravitation, the equation for force between the two bodies in the universe is given by F equal to G m1 m2 upon r square. Therefore, G equal to F r square upon m1 m2. The dimensions of G equal to dimensions of force F into dimensions of distance square r square divided by dimensions of m1 and m2. So these dimensions can be expressed as, for force, dimensions are m1 l1 t minus 2, mass into acceleration. See? For r square, dimensions are l2, and for m1 m2, dimensions are m2. Solving this, we get dimensions of G equal to m minus 1, L3 and t minus 2. These are the dimensions of the gravitational constant G. Next article we are going to study launching of an artificial satellite. How artificial satellite is launched. For launching artificial satellite, the minimum two-stage rocket is used. In first stage, satellite is raised to desired height above the Earth's surface. Earth having radius r and mass m. So from the surface of Earth, satellite is launched by using minimum two-staged rocket. In first stage, satellite is raised to desired height above the Earth's surface, where in second stage horizontal velocity is given to the satellite. Then four different cases arises. First, when horizontal velocity given to the satellite is less than critical velocity. In that case, satellite will cover certain distance and falls on the Earth's surface. When velocity of satellite is less than critical velocity, satellite will cover certain distance on the Earth and falls on the Earth's surface. This is first. Second case, when horizontal velocity given to the satellite is equal to critical velocity. In that case, the centripetal force is provided by the gravitational force and satellite will revolve in stable circular orbit around the Earth. This is the second stage. Third case, when horizontal velocity given to the satellite is greater than critical velocity but less than escape velocity, in that case satellite will revolve in elliptical orbit around the Earth. This is represented by uh, path 3 in above diagram. And last case, fourth, when horizontal velocity given to the satellite is greater than or equal to escape velocity, then satellite will escape into the space from Earth's gravitational influence. Next article we are going to study the critical velocity. Critical velocity is defined as the horizontal velocity given to the satellite revolving around the Earth so that it revolves in stable circular orbit. So when satellite is revolving in stable circular orbit around the Earth, then the velocity is said to be critical velocity and it is always denoted by Vc, critical velocity. When satellite is revolving in stable circular orbit around the Earth, then necessary centripetal force is provided by gravitational force. Now consider a satellite is revolving around the Earth. Then centripetal force is given by mvc square upon r, where vc is the critical velocity, small m is mass of the satellite, and r is radius of orbit of the satellite. Then the gravitational force is given by gmm upon r square. So centripetal force is provided by gravitational force. Therefore, mvc square upon r equal to g capital M small m upon r square, where capital M is mass of the earth, mass of the earth. So vc square is given by gm upon r. R एक कॅन्सल होईल आणि स्मॉल एम पण कॅन्सल होईल. त्यामुळे vc square equal to gm upon r. Vc, therefore Vc equal to square root of gm upon small r. Small r is radius of orbit of the satellite, therefore it is given by capital R plus h. So critical velocity finally given by square root of gm upon r plus h. This equation gives the critical velocity. The gravitational force is also given by mass into acceleration due to gravity. In that terms, the critical velocity can be obtained. The centripetal force is given by gravitational force. Centripetal force is as usual mvc square upon r equal to m into gh, where gh is acceleration due to gravity at height h above the Earth's surface. Here m gets cancelled and we get vc square equal to r into gh, that is r plus h into gh, or critical velocity vc is given by square root of r plus h into gh. So these two equations gives us the critical velocity. So comparing the right hand sides of these two equations. Comparing right hand sides of equations 1 and 2, we get square root of gm upon r plus h equal to square root of r plus h into gh, or simply gm equal to r plus h bracket square into gh. When h tends to 0, means height of satellite becomes 0, means satellite is revolving very close to Earth's surface. In that case, gh becomes equal to g. Then the equation 3 can be expressed as gm equal to capital R square into g. Now again comparing the right hand sides of equations 3 and 4, we get r plus h bracket square into gh equal to r square g, or simply gh upon g equal to r square divided by r plus h bracket square. This equation gives the relation between gh and g. So far we have studied the critical velocity. We obtained the expression for critical velocity. Now we are going to obtain the expression for time period of revolution of satellite. Consider a satellite of mass m moving along the circumference of circle with constant speed vc, critical velocity vc. Therefore, satellite is revolving in stable circular orbit around the Earth. Let capital M and R be the mass and radius of the Earth, and satellite is revolving at height h above the Earth's surface. Then the centripetal force is given by gravitational force. So centripetal force is mvc square upon r, and gravitational force is g capital M small m upon r square. Therefore, we get vc square equal to capital Gm upon r, but small r is nothing but capital R plus h. Therefore, we can write vc equal to square root of Gm upon r plus h. This equation gives us the critical velocity. Then velocity is also defined as the distance travelled upon time. So Vc equal to, in one complete rotation, distance travelled is 2 pi r and time required is capital T. So Vc equal to 2 pi r upon T. So here that T is equal to so Vc equal to 2 pi r upon T, that is equal to square root of Gm upon r plus h. We just obtained this equation for Vc. Here, instead of small r, we write capital R plus h. So T equal to 2 pi r upon Vc. So that is 2 pi into capital R plus h divided by square root of Gm upon r plus h. So here we can write 2 pi into square root of r plus h cube upon Gm. So this equation gives us the time period of revolution of satellite. So square of time period of revolution of satellite is directly proportional to cube of radius of the orbit of satellite. Now we'll study what is meant by communication satellite. Communication satellite. So there are three conditions. First, when time period of revolution of satellite is same as the time period of revolution of Earth about its axis, that is 24 hours. Okay. Second condition, when direction of revolution of satellite is same as that sense of rotation of the Earth about its axis. Third condition, when satellite is revolving in equatorial plane of the Earth, then such satellite appears to be stationary in the sky above the Earth's surface. Such satellite is said to be geostationary satellite. And when geostationary satellite is used to communication purposes, then it is said to be communication satellite. Now we are going to study the weightlessness in orbiting satellite. We feel our weight because of normal reaction exerted by Earth's surface on our body. When this normal reaction increases, we feel increase in weight, and when this normal reaction decreases, we feel loss in weight. When आपण जेव्हा जायंट व्हीलमध्ये बसतो त्यावेळी तो पाळणा खालून वरती जात असताना पोटात गोळा येतो, कारण त्यावेळी आपलं वजन आहे त्यापेक्षा जास्त असतं, कारण नॉर्मल रिॲक्शन वाढते म्हणून वजन वाढतं. तसंच पाळणा ज्यावेळी खाली येत असतो त्यावेळी परत पोटात गोळा येतो, कारण त्यावेळी आपलं वजन आहे त्यापेक्षा कमी झालेलं असतं, नॉर्मल रिॲक्शन कमी होते म्हणून. Now consider the case where astronaut sitting in an orbiting satellite. The weight of the astronaut and satellite is used to provide the necessary centripetal force necessary for circular motion of satellite and astronaut. Therefore, astronaut does not exert any force on wall of the satellite. As a result, wall of satellite does not exert any force on body of astronaut. Therefore, in absence of normal reaction, the astronaut sitting in an orbiting satellite feels complete weightlessness. Now we are going to study the Kepler's laws of planetary motion. Kepler's first law, which is also known as law of elliptical orbits. It states that all planets are revolving in elliptical orbit around the sun, with sun lies at one of the principal focus. This is the first law, Kepler's first law, which gives us the idea of elliptical orbits. Kepler's second law is also known as law of aerial velocity. The radius vector drawn from sun to position of a planet swept out equal area in equal interval of time. पोझिशन वेक्टर कुठेही असेल, समजा इथं जर प्लॅनेट असेल, हा प्लॅनेट इथून इथंपर्यंत मूव्ह झाला, तर रेडियस वेक्टरनी जो काही एरिया ट्रेस आउट केलेला असेल तेवढाच एरिया तेवढ्याच टाईममध्ये तो कायम ट्रेस आउट करतो. म्हणजे याचा अर्थ काय होतो की ज्यावेळी प्लॅनेट लांब जातो सूर्यापासून त्यावेळी त्याची वेलॉसिटी कमी होते आणि जसा तो जवळ येईल तसा वेलॉसिटी वाढत जाते. आता वेलॉसिटी इथं कंटिन्युअस सगळ्या ऑर्बिटमध्ये चेंज होत राहणार आहे, तर त्यामुळं पण ते वेलॉसिटी अशा पद्धतीनं चेंज होईल की या रेडियस वेक्टरनं स्वेप्ट आउट केलेला एरिया हा सारखाच असेल सारख्याच टाईममध्ये. म्हणजे एक्झाम्पल, इथं जर 1 महिन्यामध्ये हा एरिया त्यांनी ट्रेस आउट केला असेल तर इथं सुद्धा 1 महिन्यामध्ये तेवढाच एरिया ट्रेस आउट होतो. म्हणजे इथं स्पीड जास्त असणार, इथं स्पीड कमी असणार आहे. हा सेकंड लॉ झाला. त्यानंतर थर्ड लॉ, Kepler's third law states that the square of time period of revolution of satellite, square of time period of revolution of planet is directly proportional to cube of semi-major axis. If small r is semi-major axis, then t square is directly proportional to r cube. Now, we are going to study the binding energy of a body at rest on Earth's surface. Definition. It is defined as the minimum energy that must be supplied to body at rest on Earth's surface so that it escapes from Earth's gravitational influence. It is abbreviated as BE, binding energy. To obtain the expression for binding energy of a body at rest on Earth's surface, we have to determine total energy of the body at rest on Earth's surface. The total energy is always given by kinetic energy plus potential energy. The kinetic energy is always given by half mv square. Here v means the velocity of a body. Since body is at rest, v is 0 and the kinetic energy of a body is 0. The potential energy is always given by gravitational potential multiplied by mass of the body. The gravitational potential on Earth's surface is given by minus gm upon r, where g is gravitational constant, m is mass of Earth, and r is radius of the Earth. Therefore, potential energy equal to minus gm upon r is gravitational potential multiplied by mass of the body small m. So, which is minus gmm upon r. This is the potential energy of body at rest on Earth's surface. From the total energy, therefore total energy is given by kinetic energy plus potential energy. So total energy is minus gmm upon r. Say this is equation 3. Now negative sign in this equation indicates that body is always bound to the earth by attractive forces. So binding energy equal to modulus of total energy. So negative sign removed by modulus and binding energy is given by gmm upon r. This binding energy, when supplied to the satellite or supplied to body at rest on Earth's surface, then the body escapes from Earth's gravitational influence. Therefore, it is known as the binding energy of a body at rest on Earth's surface. Now we study the escape velocity of a body at rest on Earth's surface. Escape velocity definition. Escape velocity of a body at rest on Earth's surface is defined as minimum velocity given to the body at rest on Earth's surface so that it escapes from Earth's gravitational influence. It is always denoted by VE. When body is given escape velocity, when body is projected from the Earth's surface with escape velocity VE, then kinetic energy supplied must be equal to binding energy. So kinetic energy equal to binding energy. Kinetic energy is given by half mve square, which is equal to gmm upon r. That is ve square equal to 2gm upon r, or escape velocity ve equal to square root of 2gm upon r. This equation gives us the escape velocity of a body at rest on Earth's surface. When we substitute the values of g, when when we substitute the values of g, m, and r, then we can calculate easily the value of escape velocity. Next article. We are going to study binding energy of an orbiting satellite. Definition. The binding energy of an orbiting satellite is defined as the minimum energy that must be supplied to the orbiting satellite so that it escapes from Earth's gravitational influence. To obtain the expression for binding energy, we must obtain the expression for total energy of a satellite, orbiting satellite. The total energy is always given by kinetic energy plus potential energy. So kinetic energy is given by half mve square, because Satellite is revolving in stable circular orbit with critical velocity Vc. So kinetic energy is given by half mvc square. That is half m into square root of gm upon r plus h bracket square. So it is given by g capital M small m upon 2r plus h. This equation gives us the kinetic energy of an orbiting satellite. The potential energy of an orbiting satellite is given by minus gmm upon r plus h. The total energy is given by kinetic energy plus potential energy. So total energy is gmm upon 2r plus h is kinetic energy plus potential energy is negative minus gmm upon r plus h. So total energy is found to be negative minus gmm upon 2r plus h is the total energy. Now negative sign indicates that satellite is bound to the earth by attractive forces. Therefore, binding energy is equal to modulus of total energy equal to gmm upon 2r plus h, because modulus removes the negative sign in total energy. So when this energy is supplied to satellite, orbiting satellite, then it escapes from Earth's gravitational influence. Therefore, it is known as binding energy. Escape velocity of an orbiting satellite. आपण बाइंडिंग एनर्जीचं एक्सप्रेशन काढलं. आता आपण एस्केप व्हेलॉसिटी करता एक्सप्रेशन काढणार आहोत. डेफिनेशन एस्केप व्हेलॉसिटीची. Escape velocity of an orbiting satellite is defined as the minimum velocity given to orbiting satellite so that it escapes from Earth's gravitational influence. It is always denoted by Ve. When escape velocity is given to the satellite, then binding energy must be equal to its kinetic energy. Binding energy equal to kinetic energy. Binding energy is given by G capital M small m upon 2r plus h, and kinetic energy is half m Ve square. Therefore, rearranging the terms, Ve, we get Ve equal to square root of gm upon r plus h. दोन्हीकडे half I cancel होईल, small m cancel होईल. V square is nothing but gm upon r plus h, or Ve equal to square root of gm upon r plus h. This equation gives the escape velocity of an orbiting satellite. Now we are going to study the variation in acceleration due to gravity g with height h. We know that acceleration due to gravity on the surface of Earth is g. It is given by small g equal to capital G m upon r square. Similarly, at height h above the Earth's surface, gh is the acceleration due to gravity. So gh is given by g into m divided by r plus h bracket square, where satellite is revolving at height h above the Earth's surface, and acceleration due to gravity at height h above the Earth's surface is gh. Dividing equation 2 by equation 1, we get gh upon g equal to r square upon r plus h bracket square. Therefore, gh equal to g into r upon r plus h bracket square. That is equal to g into r plus h upon r bracket square. So, that is g into 1 plus h upon r raised to minus 2. Here we have inverted the terms and express it with index -2. So g into r plus h upon r raised to -2, which is same as gh equal to g into 1 plus h upon r raised to -2. So by simplifying this by binomial expansion, we get gh is equal to g into 1 minus 2h upon r. We are neglecting higher power terms in this equation, since h upon r is very small. So gh is given by g into 1 minus 2h upon r, where h is very small as compared with r. So this approximation is valid only for heights which are very small as compared with radius of the earth. Now we are going to study the variation in g with depth d. This is earth. Radius of earth is r and mass of earth is capital M. Then acceleration due to gravity on the surface of earth is given by small g equal to gm upon r square. So this is equation 1. G is gravitational constant, m is mass of the earth, and r is radius of the earth. Now we consider a point at depth d below the earth's surface. At this point, let acceleration due to gravity be gd. Then consider a sphere portion of a earth sphere having radius r minus d. For this radius, at this point, acceleration due to gravity is gd. Then gd is given by gd equal to capital G into m dash divided by r minus d bracket square. So a portion of earth, spherical portion of earth having radius r minus d is responsible for acceleration due to gravity at this point. The mass of this sphere is, we assume it be m dash. Then we can write gd is given by capital G into m dash divided by r minus d bracket square. This is equation 2. Now dividing equation 2 by equation 1, g gets cancelled and we can write gd upon g equal to m dash upon m into r square upon r minus d bracket square. If rho is the density of earth, then m dash upon m is given by 4 by 3 pi rho into r minus d bracket cube divided by 4 by 3 pi rho into r cube. 4 by 3 pi rho gets cancelled and we get r minus d bracket cube divided by r cube. So m dash upon m is simply expressed as r minus d bracket cube divided by r cube. Substituting this value in equation 3, we get gd upon g equal to here 4 by 3 pi rho gets cancelled, r minus d bracket cube and this r minus d bracket square gets cancelled, remains r minus d divided by r. So gd upon g is simply r minus d upon r. Therefore gd upon g equal to 1 minus d upon r, or gd equal to g into 1 minus d upon r. So as the depth increases, the acceleration due to gravity goes on decreases, and at center of earth d becomes equal to r, so r by r becomes 1, 1 minus 1, 0. At center of earth there is no acceleration due to gravity. Now we are going to study the variation in acceleration due to gravity g due to latitude lambda. Consider the point P at latitude lambda. Latitude is defined as the angle made by the line joining center of Earth and point P on the Earth's surface with equatorial plane, with equator, is known as latitude. It is usually denoted by lambda. Now consider the latitude lambda, point P at latitude lambda. At point P, P is revolving in elliptical orbit with radius small r. Small r is given by capital R cos lambda, where capital R is radius of the Earth. Then the centripetal acceleration AC is acting on point P towards the center of the ellipse. Okay? The component of AC is acting along the center of the Earth. AC cos lambda is acting towards the center of Earth along PO. This AC cos lambda is obtained from acceleration due to gravity. Therefore, effective acceleration due to gravity at point P is g lambda, which is given by g minus AC cos lambda. But AC is given by small r into omega square, where small r is capital R cos lambda. Substituting this value here, we get the acceleration due to gravity at point P. Effective acceleration due to gravity at point P is g lambda, and g lambda is obtained as g minus r omega square cos square lambda. This is the expression for acceleration due to gravity at latitude lambda.